For centuries, our understanding of light has been shaped by the idea that it behaves as both a wave and a particle. This concept became the foundation of quantum theory and gave birth to quantum mechanics. But what if this fundamental understanding could be completely reimagined? The classic double-slit experiment, introduced by Thomas Young in 1801, showed that when light passes through two narrow openings, it creates patterns of bright and dark bands on a screen. Scientists interpreted this as evidence of wave-like interference. A century later, quantum mechanics revealed that even particles like electrons could create similar interference patterns. Albert Einstein's work on the photoelectric effect showed that light travels in discrete packets called photons, and Niels Bohr developed the concept of wave-particle duality, one of the cornerstones of modern physics. Now, researchers led by Gerhard Rempe at the Max Planck Institute for Quantum Optics have proposed a groundbreaking new interpretation. They suggest that we can understand those interference patterns using quantum particles alone, without needing to view light as a wave. Their approach introduces the concept of bright and dark modes. In this view, interference patterns emerge from combining detectable and undetectable photon states. The bright states interact with observers, while dark states remain hidden. These hidden or dark photons might exist in places where we traditionally think light cancels itself out. When observers try to track these photons, they alter their state, flipping what was dark into bright, or vice versa. From this perspective, light pathways can be viewed as quantum superpositions rather than classical wave interference. As Rempe explains, this provides a quantum picture with particles of classical interference with waves. Classical physics and Maxwell's equations work well for most everyday optical events, but in certain quantum experiments, particularly when single photons interact with atoms at tiny scales, purely wave-based theories begin to fall short. This new framework places particles at the heart of interference. The wave-like patterns we observe might simply be statistical maps showing the distribution of bright and dark quantum states. When scientists try to determine which path a photon takes through two slits, they encounter the famous uncertainty principle. Observation itself can destroy the interference pattern. In this new interpretation, measuring a photon isn't just about giving it a momentum kick, but about switching a dark state to a bright one. If an observer interacts with a photon hidden in a dark region, that state might become bright enough to be detected. Rather than overturning wave-particle duality, this theory offers a purely particle-based explanation for interference while maintaining quantum superposition. On a philosophical level, we might need to shift our mental picture toward probabilities of bright and dark particles, although most institutions will likely continue teaching the wave framework as a useful approximation. This updated model could lead to detecting light in places once thought to be voids. Novel sensors might probe areas of destructive interference, potentially leading to futuristic optical technologies. Experimental physicists may look for traces of photons in dark states, and if these photons can be coaxed into bright states without disturbing other properties, entirely new measurement techniques could emerge. This research opens the door to questioning what other fundamental assumptions might change under quantum scrutiny. Researchers are already trying to extend these ideas to larger-scale experiments, including matter waves and possibly even gravitational wave detection. Critics note that wave-based models still work excellently at larger distances. This new quantum picture becomes essential only when dealing with single particles and atoms. Whether this new interpretation replaces or complements our classical understanding remains an open question. the next big debate in the fascinating evolution of quantum physics. Find the full article on Earth.com in the description.